So, like all good math classes, there is some theorems about the existence of a unique solution. It turns out as long as we can justify certain parameters, then we can guarantee there is a unique solution. So you can kind of see that our theorem here states that we have a rectangular region of parameters A, B, C, and D. And I'll kind of scroll down here so you can kind of see the picture a little bit better. All right, and it contains a point on the interior of this region. Then if a function and its derivative are continuous in that region, then there exists an interval such that there does exist a unique solution. So as long as we have something within that, some sort of defined interval, then we can guarantee there is some sort of uniqueness. So it is possible. Okay, so let's revisit that last question we had where we found there were two functions that satisfied that differential. And let's kind of consider what's going on here. So if we look at, say, switch colors, I'm going to go back here. So let's say our function is xy to the 1/2 power. And then I take the differential with respect to y, so f df dy, right? So now I'm doing a partial derivative with respect to y. So I'm going to treat x as a constant, so that's 1/2 x of y to the negative 1/2 power. All right, so what would that look like? Nice and pretty. That would look like x over 2 to the y to the 1/2, right? And so this is kind of where we get to the uniqueness element. Because according to that theorem, it's got to satisfy, it's got to be continuous and differentiable in both the original function and its derivative. Now, in this case, we have a restriction. We can't let y equal 0 at that particular point. So we are limited to making sure that y has got to be at least something greater than 0. So as long as we can satisfy that condition, then we can guarantee there is a unique function. So we sort of get away from the that last case where we had two potential solutions. Okay, so in this this next example, we're asked to find the solution of a first order IVP consisting of a given differential and the initial condition. And then we're supposed to identify the largest interval over which the solution would be defined. Okay, so they gave us a differential, but they also gave us the original function, and they gave us that point of y of 1/2 equals -4. So let's evaluate that. Let's see if we can find a value of c that would satisfy that initial point. So that would be when y is -4, we got 1 over 1/2 squared plus c. So that's -4 equals 1 over 1/4 plus c. And let's do some good old-fashioned algebra rules here. So I think I'm going to multiply everybody by 4. So that'll give me -16 equals 4 over 1 plus 4c. I feel like I need to write that out. It's all my college algebra days teaching that class. So I'm multiplying everybody by 4. And then let's see if that simplifies down to give us anything interesting as far as the value of c goes. You know what? I think I made this harder than I need to. Alright, so find the solution of the first order IVP consisting of this differential equation and given the initial condition, and then give the largest interval over which the solution is defined. Okay, so we kind of lucked into the fact that they gave us the initial function and they told us the point that it goes through. So let's see if we can find c. So that's 1 over 1/2 squared plus c, which is -4 equals 1 over 1/4 plus c, and I'm going to do a little bit of fraction rules here, so I'm going to swap that out. So 1/4 plus c equals 1 over negative fourth. Let's see, so that would mean I want to subtract off a fourth. And so that says c equals negative a fourth minus a fourth, which is negative 2/4, which is negative a half. Okay, so our function looks like 1 over x squared minus a half. And alright, so what do we have? We have the equation that satisfies that differential, and then we just need to come up with an interval. So what I want to avoid is let's see, we got a fraction in this case, so I want to make sure that there's I don't end up with let's see, I'm going to figure out where that's going to equal 0, and actually I'm squaring something, so in solving that I want to make sure I end up with something positive. So I want to make sure that stays positive the whole time. Not only that can it not equal 0, but it can't be a negative value of x. So that would be x squared is greater than 1/2. So that would be x is greater than plus or minus 1 over the square root of 2. So that says as long as I stay with something, let's see, 1 over, let's think about this on a number line. Positive 1. Okay, so if I go outside of the 1 over square root of 2, what's going to happen to my function here? See, I think we need to stay inside it. So I think we're looking at the domain of somewhere between on the inside. So as long as I stay on the inside, then I'm guaranteed to get a positive value, and once I get outside of that, then I can't promise it's going to be positive. So I would say the interval would go from negative 1 over square root of 2 to positive 1 over square root of 2.